Hello and welcome back to Calculus 3, section 12.9, Lagrange Multipliers. So this is the last section, and I guess you voted to have the test after this, so yeah, good luck with that. We have another section when we are going to look for extreme points, meaning min and max. And for these guys, now we're going to add constraints. So imagine having an object, think of a hill, right? And there is a road or some kind of path that is waving along the side of the hill. Well, you observe that road, and at certain points that road is going to have a maximum elevation and then the minimum elevation for the portion of the road that you're observing. Not sure if I can really draw something, but let's say there's a path like this, right? So you're observing, and here's the max value, and let's say this is the min value, right? Well, first of all, I do have an equation that describes the surface of the hill. So we'll call that z equals some kind of f of xy. And then I'm going to also have an equation which will describe the g of xy equal to 0 that will describe this path. And then these two equations together, working together, because remember, the path is on the side of the hill, and then path has its own equation. So I can make a different path, right, which will change g but will not change f. So we are not looking for the maximum point on the hill. That was the previous exercise. I'll just put this path. All right, this is some kind of path you're walking. Path. There we go. Much better. So what would be the way to compute something like this? Well, we are going to introduce Lagrange multiplier lambda, which is going to add an extra degree of freedom. And the interesting thing about this, I mean, in mathematics generally, when you increase the number of dimensions, you make your present calculations easier. That is, I don't know how much you know about it, but complex variables, complex analysis, complex numbers, and all of that kind of stuff. Yes, it's called complex, which is really an unfortunate title because it really simplifies mathematics greatly. You go from the one-dimensional number, which you are used to, like number 7 or pi over 2, to a two-dimensional number, which is like 3 plus 4i. So now you have an extra dimension. So your good old function y equal f of x becomes a four-dimensional function because you have a two-dimensional input and two-dimensional output. Vastly more powerful. So that crazy integral that you had in Calc 2, if you remember, I call it the evil integral when I teach it, e to the x sine x dx, where you have to take integration by parts twice and then know the trick to move to the left and right? It takes a page to solve this. Complex variables solve this problem in 3 steps. 2 lines, that's all you need, 3 steps. It is, so anytime when you raise number of dimensions for your calculations, you greatly simplify calculations for us. So what Lagrange multipliers are going to do is exactly that. We are going to introduce the parameter lambda, and that brings us an extra degree of freedom. And then when we start solving equations, that lambda will sometimes help, and sometimes will be in a way, but we can always eliminate it. And that's something that that helps out. So also, from the theoretical point of view, what I'm going to do is I'm going to equal the two gradients here. And the two gradients will have to have the same value, and they should be actually this parameter lambda, which is our Lagrange multiplier. They should be that lambda serves as the constant multiplier that allows us to equal the two gradients. So what is the method for Lagrange? And this works for any dimension. Lagrange multiplier simply says gradient f is equal to lambda gradient g. This is going to give us all equations except the last one. And then you also need g of whatever amount of variables you have over here equal to 0. This is going to be system of equations to solve, and that will give you the points that are min and the max, or max, I mean, not n. So this is your method of Lagrange multipliers. You simply solve the system. Simply. Many times that system is, 4 by 4 with non-linear terms in it, so yes, it can be a living nightmare to solve. But yeah, again, works for any number. When they talk about this in a textbook, they give you the 2-dimensional version, then they give you 3-dimensional version. I'm just telling you that this works in any number of dimensions. So we are going to do only 2D and 3D, obviously, but it works also for 17D if you want to. So let's do some of the vanilla examples to get used to the method. For instance, Lagrange multiplier, let's start with problem 6. Those multipliers that are worked out in a textbook, obviously read through those to get familiar. I'm just going to work out extra ones so you can have more of these. All right, so this is our surface, guys. This is the hill, okay? And then I need the path, and that is going to be the x squared plus y squared equals 1. So this is the unit circle. And okay, let me give some names over here. So this over here is called the objective function. And that's going to be your f. And this one over here is called the constraint. Known as G. So now, to work on our Lagrange, we need gradient of f. Gradient of f, remember, that's the vector of all partial derivatives. So partial of x is just y squared, and then partial of y is 2xy. Now, we would write from here that g of xy, you put this in the implicit form, is x squared plus y squared minus 1 equal to 0. If you go back to you see how it's equal to 0 over here? 0 is the implicit form. And now, when everything is on the left, you can find your del g. Partial derivative in respect to x is 2x. Partial derivative in respect to y is 2y. So step number 1 is to actually write the g implicitly, and then so that you can take the gradient. Right? Why is this important? Well, in this case, yeah, it was simple, and 1 would die either way if you take the derivative. But what would you do if you had, let's say, xy squared equals to sine x, right? How do you take the derivative of this when there is equal in between? So your job is to move sine to the other side, make it equal to 0, and then take the derivatives. So please remember that your job is to first create the constraint function so that g equals everything else, which is implicit form, and then you can take your partial derivatives to form the gradient for g. And now we are using the formula which says del f equals lambda del g. So what this equation, so this is the Lagrange, right? Lagrange equation over here. So what I'm going to do now is I'm going to say, well, I'll write it out. You don't have to write this in the future. I'll put the del f is equal to lambda del g. And now you know that these guys distribute, right? So lambda will distribute. And you will have 2 lambda x and 2 lambda y, because that's just a constant that distributes inside. Great. This is the equation here, which is going to give you equations. Y squared is equal to 2 lambda x. 2xy is equal to 2 lambda y. You have x, y, and lambda. You have 3 variables. You need one more equation, and that's going to be your g equation, which is x squared plus y squared equals 1, or you can go minus 1 equals 0. So whatever. So the procedure which I gave you earlier, so these equations are coming from del f equals lambda del g. And this equation here is your g of x blah 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 is equal to 0. Now you need to solve this. No one cares what methods you use. Now, for most practical purposes, I will always ask you to first attack lambda, because lambda is the only thing you don't need. It's supposed to be there to help us solve these problems, and if you calculate that lambda is equal to 2, no one cares, because it doesn't serve any purpose in the answer, which will say that the minimum point occurs at x, y location. So there's no lambda mentioned in there. So if you can eliminate lambda, that's your first order of business. Now, first off, I am going to ask you not to divide and cancel things. So do not go in a second equation and say, oh, cancel y's. Sure, you can cancel 2's. That's okay, right? 2 and 2 will cancel. But you can't cancel y, because in order for you to cancel y, that means that you have to divide y on both sides. But what if y is 0? Right? You don't know what y is. So you can't go and cancel y's and just hope, right, that everything will work out. So we have to be obviously more careful with how to solve these equations. So there are a few things that we can explore. First one is there a way for me to get rid of this lambda? So if I write lambda is equal to, and then I move 2x to the other side, right, then I'm technically dividing by x, but I didn't cancel any of the x's, right? So that's one way, but we can also take the square root of y squared, which will also introduce plus minus on the right-hand side, which also is not the greatest thing we can possibly do. So let's see, and again, there are no rules on, or steps to follow. It is just playing with these equations until you actually get the solutions out. So what am I going to do first? Well, from the first equation, I'm going to say that lambda is equal to y squared over 2x. I'm not canceling any x's. I'm not, Now, I am saying with this statement over here that x is not supposed to be 0, but once I plug that for the other lambda in equation 2, maybe I should label these equations as equation 1, equation 2, and equation 3. So this was equation 1, and now I'm going to write equation 2, where I have xy is equal to lambda is y squared over 2x times y. And now observe that I'm going to multiply both sides by 2x. So I'm having 2x squared y is equal to y cubed. So now this is my new equation 2. I can label it 2 star, I guess. And then I still have my equation 3 as is. I haven't done anything with that. It's x squared plus y squared equals to 1. So this is my new system, these two equations. And whether this is going to work or not, I have no clue. Let's see what else we can do. I'm going to now, from this equation, solve for x squared, get y cubed divided by 2y. I'm again not going to cancel now. But actually, you know what we could do? That trick so you can cancel is you can also assume solution of 0, 0 and then check if that works. If that solution works, 0, 0, you will keep it. If it doesn't work, you will throw it away. So that's a hack way to actually be able to cancel these kind of things. Now that I solved for x squared, we plug that in here, and I have y cubed over 2y plus y squared is equal to 1. Now, check 0, 0, so we don't have to worry about cancellation. So we'll deal with that. What do I have? I have 1/2 y squared plus y squared is equal to 1. That is 3/2 y squared is equal to 1. Y squared is equal to 2/3. And finally, y is equal to plus minus square root of 2/3, which is square root of 6 over 3. When you rationalize times root 3, you get square root of 6 over 3. So, and plus minus, right? So we have two y values, and then we can go back and calculate x's. And we have to also check 0, 0 because they eventually gave in and just canceled y's. I have equation somewhere, there it is, which relates x and the y. So this equation here says, what should I call this equation? Let's call this equation 4. So equation 4 says that x squared is equal to y squared over 2. X squared is equal to y squared over 2. And I know that y squared is 3. Don't use this for no reason, right? You already have that the y squared, so just swap that in. So x squared is equal to half of this. So 1/2 of 2/3, which is 1/3. From where x is equal to plus minus root 3 over 3. So what do I have as solutions? I have, well, 5 points. I still haven't checked 0, 0. I have 0, 0, which I have to check. And then I have root 3 over 3 with root 6 over 3. Root 3 over 3 with negative root 6 over 3. Then I have negative root 3 over 3 with root 6 over 3. And negative root 3 over 3 with negative root 6 over 3. Those are 5 candidates. Oh, this is how basic problems look like, by the way. There's only 2 variables in there, right? X and a y. Well, 3 with lambda, sure. So now, what do? I want to know maximum and minimum. Please observe that this is a finite object. finite object means that I'm going to have the absolute max and absolute min. All it takes is to plug these points in one by one into your original problem and figure out which one of them will have the lowest x value, lowest z value, and which one is going to have the highest z value. Those are going to be your absolute min and absolute max. So now, to finish this off, we have the equation z equals f of x y, which was xy squared, I believe. Yep. And zf of 0, 0 is going to give us big fat 0. So that's a point 0, 0, 0. The next one is going to be, I can keep writing z equals, if that makes you happy, of root 3 over 3, root 6 over 3. Now, copy x as is, which is root 3 over 3, and then square the other one, which is 6 over 9. So now this will cancel, and then I have 2 root 3 over 9. Z of f of root 3 over 3 negative root 6 over 3. When I square this value, we get the same. Then z equals f negative root 3 over 3 root 6 over 3. That's going to be equal to negative root 3 over 3 6 over 9, which is negative 2 root 3 over 9. And finally, z equals f of negative root 3 over 3 negative root 6 over 3, which gives us another one of these, negative 2 root 3 over 9. So I find that these points here are minimum points. We have root 3 over 3, root 6 over 3, and 2 root 3 over 9, and root 3 over 3, negative root 6 over 3, 2 root 3 over 9. So both of these are max each. Absolute max, right? Because the z value is the highest. Now we had 2 points. That's fine. Remember, the sine function is reaching 1 many times, and each one of those is the absolute max. So yeah, you can have multiple points that have the same value. Then we have negative root 3 over 3, root 6 over 3, negative 2 root 3 over 9. And negative root 3 over 3, negative root 6 over 3, negative 2 root 3 over 9, both of which are minimum.
Feel the carpal tunnel just coming up.
Yeah, this is a quick example. So please, next time when someone figure of speech goes, what do you know? Lagrange? What do you know? Right? There should be immediate answer, and then show them the simplest problem that could be there, right? I mean, this setup for our f of xy didn't even have the inverse tangent or ln or e to the xy or whatever like that, right? It was just x times y squared, and there you go, right? We have 2 pages of bliss. Let's enjoy another one of these. Would you pick a problem before you leave, or no?
What number?
From 6 to 14? 14 it is. Amazing.
Oh.
Lock the doors. F of xy is xy plus x plus y. See? Nothing to worry about. Subject to xy, x squared y squared equals to 4. Right. Let's see what you are going to do. Mm-hmm.
Is it your phone? I don't know. I don't even remember. No, I'm just. You know how I was like, pull out. Can't see the gas inside. Or whatever. I just can't say stuff. Oh, this is. You got to that too so far. So three equations. Get three equations. That's right. I think so. I have 2 points. And I just don't want the question So when will we use this in real life?
Coming up.
Coming up?
Mm-hmm.
Is that what you just tell everyone?
No, it's coming up in about 20 minutes. Let's take a look at this together. So I need my partial derivatives. So fx is going to be y plus 1. Fy is going to be x plus 1. At this point I go, yay, symmetric. Then, well, so far it's symmetric, so we'll see. So now I need to write my g of xy as x squared y squared minus 4 equal to 0. So now I have to compile del f equal lambda del g. So f is the partial derivatives here, which is y plus 1 and x plus 1, equals to lambda, and partial derivatives here is 2xy squared and 2x squared y. So now when I'm writing my equations, I have that y plus 1 is equal to 2 lambda xy squared, and x plus 1 is equal to 2 lambda x squared y, and also x squared y squared is equal to 4. I'm going to box these equations because these are my equations to solve. Now clearly solution for something like this is positive negative root 2, so you just keep moving on with the testing and that's it. I had to put in the word clearly because, you know, it's obvious. So what do I have? If you observe the top 2 equations, they're symmetric, right? They're symmetric, and this equation itself is symmetric. What does it mean being symmetric? It means if you swap x or y, you get the same thing. So if I replace all x's with y's and all y's with x's in the top equation, I will get the bottom equation. Let's try that. So it's going to be an x, and then a y, and then x squared. Isn't that exactly the equation below? Right? So that's the trick. You are looking for symmetric equations if possible. So because of the symmetry, that's a really good thing, right? So symmetry over here. Symmetry yields that x is equal to y. Now, as soon as you have x equals to y, you can ignore all the equations, work just on the bottom one, right? Because that immediately is that your right, so you will take that into the bottom equation, get x squared equals to 4, x to the 4 equals to 4, x equal 4th root of the 4, which is plus minus root 2. I did say clearly. It was obvious. It was obvious even when she picked the problem, it was obvious.
You could have just looked at the path and then. Yeah.
So now I have that x. Now also x is equal to y, which is also plus minus root 2, which is going to give me 4 points, root 2, root 2, root 2, negative root 2, negative root 2, root 2, negative root 2, root 2, negative root 2. There we go. Now we have our z which is f of xy is to be xy plus x plus y. So now z of root 2 is going to be 2 plus 2 root 2. So we have root 2, 2 plus 2 root 2. Next one, z is root 2 negative root 2. Well, that's going to give me negative 2, and then these guys die. So root 2 negative root 2 and then negative 2. Then the next one, z is f of negative root 2, which is symmetric, so it's another negative 2. So negative root 2, negative 2. Z equals f of negative root 2 equals 2. That's a 2 minus 2 root 2. So negative root 2, 2 minus 2 root 2. So without any thinking, right, this must be max, because you have 2 plus 2 root 2, and this is 2 minus 2 root 2. These are negative numbers, right? So these three are negative. All three are negative because 2 root 2 is more than just 2, so that's negative. I don't care how much it is, it's just negative, right? And clearly, this is almost like 2 minus 2 is 0. 2 minus a little bit more than 2, right? But this is less than 2. So these are minimum. But then you can work your decimals if you want to and get your values. Well, clearly. But let's do some of the, heavier stuff. Problems 15 through 24 are f of x, y, z, which once we include the Lagrange multiplier lambda, we are bringing it up to 4 variables, 4 equations, so that should be more fun.
Is the fourth one a maximum as well?
No, that one is in between. We are only looking for absolute min, absolute max. Which problem, 15 through 24?
21.
21 it is.
21.
F of x, y, z is given as 2x plus z squared. Sheesh. And then we have the ellipsoid over here of the x squared plus y squared plus 2z squared equals to 25. Yeah. You know how much symmetry you're going to have here? Exactly.
So much of none.
So much of none, exactly. Have fun. I have nothing new to teach. It's still the same equation. Del f equals lambda del g works for any dimension, right? So if I had 17 points, hey, it will be 18 by 18 system, right? Now you're looking for 3 partial derivatives. You will have 4 equations when you involve g, and then you have to plow through all that stuff to get x, y, z's. Now this is going to be like W equals, right? So you're looking for the W to be the smallest number for minimum and W for the largest number for the maximum.
Well, yeah, I got 2. Yes. 1.20 is z squared. First derivative z squared. 2z. I mean 2z. Oh, I didn't write down that was squared. I just wrote my z back.
I said nothing. All I said is have fun.
Developing carpal tunnel. What is the actual diagnosis of carpal tunnel? Like, what happens to you? Like your hand just cramps up and it hurts a lot?
Yeah.
Yeah. That's. Is it like a condition or just kind of just happens after you've been writing
Just
for a
look
long
it up.
time?
I don't know. I don't have it.
I have to figure it out. I have to find it out myself, right?
Exactly.
I'm not sure what I'm doing. Oh, yeah, no. I just got here. Did you get these? Yes. Yes, it's a bit of salt for the things now. Yeah. Real without and stuff. I'll let that support. Why did you choose divide by 2? One equals yes. So then you can say like 1 over 1 over x. No. I'd love to hear Benjalawi single.
Oh my god.
I bet it would be amazing.
What is it?
I think it's French. Yeah. Lagrange is definitely a French word.
That's not how it's supposed to sound.
I'm gonna go to his office and just ask him.
He is so like adorable. He's so cute.
Oh my god, that'd be great. Is that what you dream about at night? And then your grandpa? That's all I have to say. What did you try this one?
Yeah, I got y equals 0 because it right, because you lost your y, right?
Oh, I did lose my y. Wait, I mean, I kept going. And then I kept going.
Wait, what'd you get for x? Or what'd you even get?
I'm still working on it.
I lost my estimates.
So what? I'm looking at it.
So lambda equals 1 over. Yeah. Then you plug that into y. Okay, and I plug lambda into c. Yeah, and then I got 2z equals 4 over x times z. Yeah, no, my mom's like that. And then I got x equals 2z over z. Yeah, and then I plugged it into the this, but then it was a whole mess. I got z. Yeah, I just plugged it in as this is wrong. I just canceled. Sorry, you can sell. I can lose.
Alright, so you can solve that.
We have a skunk duck that's all by
All right.
4z over x, right? Did you say that? And then you could multiply by 1 over 4z.
Why?
Did you guys like do this?
I keep getting caught from like why or you know why? Okay,
Yeah, I didn't
get that.
Because if lambda was 0, it would mess everything up.
I said lambda, yeah.
I said lambda 1 over 6.
I have to get rid of variable.
So, well, I just got rid of z equals 1 over z.
Oh, so you just
But you can't, I don't think you can do that because what if z equals 0?
then you just have to test it.
Yeah.
So if lambda equals 1 over x and lambda equals 1 over 2, then x equals 2.
I did get x equals 2.
Y equals 0.
I just got rid of my z's.
1. Either 1.
Did you do the test? Wait, did you check if 0, 0 was valid? Or whatever?
No.
You'll check it later.
I'm not even checking if 0, 0 is valid or not valid.
You check it later. I don't know how you check it.
Plug it into G. Plug into G. See, make sure.
Let's see if it.
That's what I said.
Oh, yeah?
Oh,
Yeah, if you were listening to me,
Oh, yeah, I guess I'm just not listening.
X divided by x squared in theory, x equals 0, and this is undefined. Just have this down. Now we're in limbo.
You're mad, wait, so you're mad about this part? That's the other
Yeah, because you can't divide by x. You say you can't.
No, you can divide by x, you can have like
No, the reason you said that is because your variable might be 0, which is get
All right, so do you all have the same equations? Do we all have the same equations?
Yeah.
As far as
Now, is it clear that from these equations, is it immediately clear that the y is equal to 0?
Yeah.
Yes? Good. Well, you just reduced the system down to technically nothing. So from this equation here, we have that y is equal to 0. The top equation tells us that lambda x is equal to 1, right? From where lambda is 1 over x. And we can plug that here and kill lambda. So I have y equals 0, and over here I have that z is equal to 2z over x, and we also have x squared plus 2z squared is equal to 25. I have we all good? So there you go. Yeah, lambda is not 0, because if lambda is 0, you're getting trivial solution 0 equals 0.
All right.
Remember?
That's where I was.
All right, good. So if z is not equal to 0, if z is not equal to 0, we have that x is 2.
Yes.
Right?
Yes.
And then if x is 2, then this becomes 4, 21, 21 over 2, so square root of 42 over 2. So if z is not 0, I can divide both sides by z. And then you have 1 equals 2 over x. You multiply x to the other side, x equals to 2. You see the if over here? I don't know if I can. I'll move it closer. You see it? So now, x equals to 2. That goes in here. Y is already 0, so I killed y already. So that's 4 plus 2z squared is equal to 25. 2z squared is 21. Z squared is 21 over 2. Z equals plus minus square root of 21 over 2, which is plus minus square root of 42 over 2. So, 2 points, 2, 0, and square root of 42 over 2, and 2, 0, negative square root of 42 over 2. So now we have that, let's say w is equal to f of x, y, z is equal to x plus z. So what happened?
Dumb question.
So now w is equal to f of 2, 0 square root of 42 over 2 when we plug that in, we get 4 plus 2 times 42 over 4. So the whole thing is 25, right? And W of f of 20 negative square root of 42 over 2 is going to be, again, when you plug here, 2 times 4, 2 times is 2, plus 0 is there, and then plus, when you square, we get the same thing. So no min values, just the max values.
Why can't we do
What about when we got rid of the z? You have to do like a 0 to or something.
What happened? Oh. All right. Well, that's going to change stuff a little bit. So 42 over 4, that's 21 over 2 plus 8 is 29 over 2. So both points are max.
How do you know the max one?
Yeah, but now let me see what's happening with the fxx. Oh,
Like,
fxx is 0.
oh. Did we just see that entire thing?
Do what?
So what happened with that? Figure out.
No, I was hoping to claim quickly why these are both max points, but they might not be. All right, let's.
Because I don't think that has a max. Because everything's positive.
The answer is I don't know yet.
Okay.
Eventually. Now, if z is equal to 0, then x squared plus y squared plus 2z squared equals 25 gives us that x is equal to 5. And we know that y is equal to 0 already. So we have a 0.500. So the entire problem here was under condition that z is not 0 because we have to divide by z over here. Right? We divide both sides by z and then we calculate that x is 2. So we made the assumption that z is not 0. Now if I make the assumption that z is equal to 0, I can't get anything out of this equation because 0 equals 0. But I can get stuff out of g equation because g equation, as you can see, if z is 0 and we know y is 0, then x is plus minus 5. Oops. So x is plus minus 5. So I have these 2 points to consider now. In addition, so w of f of 500. I keep losing this. Okay, there it is. So that's 10. And w of negative 500 is negative 10. So here's your min. It's a negative number. These two are max because they're more than 10, right? That's almost 15. It's 14 and a half. Right, this 14 and a half. So they're both max and max value. And then there we go. Whee! Right? Now, one more problem, and let's do a word problem this time, because, as I said, this is finally a section that can make you money. So we take a look at the application. Your project does have, I already said, Lagrange application on it. And we can go from there. Shipping regulations, box with minimum surface area, extreme distances to an ellipse, maximum area rectangle in an ellipse, maximum perimeter rectangle in an ellipse. So which one should we? Minimum distance to a plane, minimum distance to a surface, minimum distance to a cone.
All these things?
Oh, is this that? Like cone for the sphere?
It says minimum distance to a cone. Shall we do that?
Let's do it. Yeah.
Box with minimum surface area, extreme distances to an ellipse. The ones that I like is the maximum area of the rectangle inside the ellipse and maximum perimeter rectangle inside the ellipse. Those are cool.
Pick the one that's going to be on the test.
Let's do the area.
I don't know. The test is Thursday, right? I still have 2 days. All right, let's take a look at the area in the ellipse. So then I don't have to put this one on the test.
You should put the perimeter one on the test then.
Find the dimensions of the rectangle with maximum area that can be inscribed. Guys, are you paying attention at all?
Yeah.
In the ellipse given by 4x squared, yes, plus 16y squared is equal to 16. No coffee. So, situation is as follows. I have an ellipse and I have a rectangle inscribed inside, and then we want to find, so if I label this point over here xy, we want to find the dimensions of the rectangle that will have maximum area. Wow, this problem can be done actually even in Calc 1. I guess exam 3. Anyway, so what we have now is if you label this point xy, then this distance over here is x, and this distance over here is x, making the length of our rectangle 2x. And this would be y, this would be y, making this 2y, so that the area equation is 4xy, because it's 2x times 2y, and we want that to be a max, right? And then we also have the ellipse equation over here. So that's, if you cancel by 4, we have x squared plus 4y squared is equal to 4. Now, this equation is your f equation, this equation is your g equation. Right? Objective equation is the one that you are minimizing or maximizing, and constraint equation is the one that it's given because you have to work within those constraints. I hope that you can see the language of the problem. It says, find the area, maximum area of the rectangle. If I didn't constrain that, right, inscribe that inside the ellipse, it's infinite, right? The rectangle. So the rectangle is constrained by the ellipse. So ellipse, equation of the ellipse is the constraint. All right, so what do I have? I have f of xy to be 4xy, and I have g of xy to be x squared plus 4y squared minus 4 equal to 0. So now I have partial x, which is 4y, partial y, which is 4x, is equal to lambda. Yeah. There we go. Lambda, that's 2x partial derivative of x and partial derivative by 8y. Perfect. So now, equations. 4y is equal to 2 lambda x. 4x is equal to 8 lambda y. And x squared plus 4y squared is equal to 4. I'm going to box this system. Need to solve the system over here. No coughing. Now we have 2y is equal to lambda x. X is equal to 2 lambda y. And x squared plus 4y squared is equal to 4. These are not symmetric. What did I just say? So what should we do? Well, we can solve for lambda and get 2y over x. Then my equation 2 becomes x equals 2 times 2y over x times y, from where x squared is equal to 4y squared. Now we plug that into equation 3. So equation 3 now becomes, instead of x squared, I have 4y squared plus another 4y squared is equal to 4. Divide through by 4, and the answer is obviously again square root of 2. So this is 2y squared is equal to 1. From where y is, square root of 2 over 2, right? It's 1/2. So y is plus minus square root of 1/2, which is root 2 over 2. Now, we take the equation x squared is equal to 4y squared, and we plug this one in. So x squared is equal to 4 times 1/2, which is 2, and x's are plus minus root 2. Ellipse has, there are 4 corners. But I calculated x's that will yield the maximum. I calculated x to be root 2 and y to be root 2 over 2. So what are the dimensions? This side is 2x. So that's going to be 2x. So it's 2 root 2. And this side is 2y, which is root 2. So dimensions of the rectangle are going to be 2 root 2 by root 2. Now we do have also negative root 2 and negative root 2 over 2, but we don't care about it because these are distances, right? Distance is always positive. So if I go, right, this is going to be, x is root 2, right? Oh, I wrote it backwards. No one said anything. It's like, you guys don't care. It's supposed to be root 2 by 2 root 2. No. By. Oh, no, I had it right.
Yeah.
Because you have to multiply it by 2.
So we do care.
2 root 2.
Maybe that's why you didn't say anything.
Yeah. Okay, good. Great. So that was the word problem. Do I have something more interesting than this? Temperature on elliptical plate. See? They have some of the cool stuff that you guys can enjoy.
Hey.
Problems is for horses. 62 to 65 are problems that have multiple constraints. So that just adds more equations.
How would you solve that using calculus? You have to make like a square and circle.
Same thing. You have the equation. You just so you have your equations, and then you plug one variable into here, and you take the derivative. I'm not sure why is this right. You can solve this one, this constraint. You can solve it as x equals 4 minus 4y, the square root, and then you plug that for this x over here, and then you differentiate that equal to 0. So calculus 1 does solve this problem as well. Have to get the same answer. You can enjoy that at home and see that you get the same answer. And that's chapter 12, guys.
Oh.
I know, right? So that's that for now. What, the stream died? No one is paying attention. So all of this is probably gone. I asked for someone to watch the stream as the lecture goes on.
That's what happened in your last lecture today.
Yeah. All right. So I'll just say bye.